Did you know solid, liquids, and gases are not the only states of matter we have in this universe? Professor Bose at the University of Dhaka in India was a physicist that was studying statistical principles of particles, focusing on particles that did not follow Pauli's exclusion principle. He was very interested in this topic, but nobody paid attention to him. So he sent his paper to Albert Einstein, which found it very interesting. Einstein published Bose's paper and further published a paper of his own, making this state of matter the Bose-Einstein condensate.
To understand Bose-Einstein condensate, we must first understand two basic principles: fermions and bosons. Fermions are particles that have half-integer spin, for example 1/2, plus minus 1/2, plus minus 3/2, etc. They follow Pauli's exclusion principle, which means they cannot occupy the same quantum state. They are produced and undergo particle-antiparticle annihilation. Some examples of them are electrons, protons, neutrons, and muons. In contrast, bosons have integer spin, plus minus 1, plus minus 2. They do not follow Pauli's exclusion principle, meaning they can occupy the same quantum state. As a matter of fact, they prefer it. And there is no limit to the number of how many particles can occupy the same quantum state. They are governed by Bose-Einstein statistics. Some examples of them are photons, gluons, and mesons. It is important to highlight that composite particles can also act as fermions or bosons.
Helium is an element with really interesting properties. It has the lowest boiling point with a 4.2 Kelvin at 1 atmosphere. It is also used as a cooling device, but it is most interesting when it itself is cool. Canneling ounce measures the density of the liquid helium at really low temperatures as a function of temperature and had these results. It can be seen that this graph has a peak, and then from 2.17 Kelvin to 4.2 Kelvin, this liquid is boiling, but from 2.17 Kelvin to 0 Kelvin, the liquid is really calm. We cannot reach absolute zero, obviously, because of the third law of thermodynamics. This is a fact. We can see that in 2.17 Kelvin, because of this interesting behavior, it is the critical temperature. Physicist Mark Semanki made a measurement of the rate of flow of the liquid helium on a capillary tube on a function of temperature. He noticed that below the critical temperature, the fluid was behaving as a superfluid, and above the critical temperature, it was behaving as a normal fluid. The really interesting part of this is that on the superfluid, the viscosity was much less than on the normal liquid. When the viscosity was near zero, some weird properties started happening, called as the creeping film.
It appears to defy gravity. A thin film can climb walls and escape its container.
Another experiment was to measure on a metal plane that was on the surface of the liquid helium to measure the drag of this metal plane. The interesting part here was that the liquid acts as a normal liquid and not as a superfluid. This was a contradiction with the previous experiment. So last time we were discussing a contradiction on the experiments. That is when Fritz London proposed a new theory in when the helium liquid was part superfluid and part normal fluid. So in the experiment of the caterpillar, that was something like this, and the helium fluid was on this base, it was dripping with a greater rate of flow, only the part superfluid. So this part of here was a superfluid.
But the moment the helium turns superfluid, it leaks through.
But on the other experiment, when you had a plate, a metal plate, this is the metal, and it was dragging it with the liquid helium, the part that was creating the more friction, acting with more viscosity, acting like a normal fluid, was this part. So this part was the normal fluid, no liquid, and the other part was the part of the superfluid. The theory of London, mathematically, was that the fraction of the part of the superfluid was given, this is the fraction of the superfluid, 1 minus the temperature over the critical temperature to the 3/2. And this will determine what fraction of the superfluid is on the whole liquid helium. The closer we approach to 0 Kelvin, absolute zero, the helium liquid will have a greater part of superfluid. So in theory, when we are on absolute zero, that we cannot reach it, this liquid will be 100% superfluid, superliquid, sorry. And this is what we call, this is a great example of a Bose-Einstein condensate.
Bose-Einstein condensate is a state of matter that is a collection of particles cooled down to near absolute 0 Kelvin. This collection of particles coalesce into a single mechanical quantum entity. This single entity can be described as a single wave function. This is very interesting for engineers and physicists because they can better understand quantum mechanics. Although this state of matter was first theorized in 1925, it was only synthesized until 1995. It was done by scientists Carl Wieman and Eric Cornell in a conjunction of the National Institute of Standards and Technology and the University of Colorado. They did this with a dilute vapor of rubidium.
Well, explaining Bose-Einstein statistics is not an easy task. However, I would actually like to tell you that there is a way to tell what the population is at a given energy level. However, we struggle a little bit because everything looks the same. For normal particles, usually what we do is just measure the amount of levels of energy based on what we already have, because all of the atoms should have a different level of energy based on the Pauli exclusion principle. But as we know, most Einstein condensates do not follow that principle. So what do we commonly do with the original? We actually follow this little distribution right here, which is actually dependent on the amount of energy that we have in that level. We subtract that from that the chemical potential, and we divide it between the constant of Boltzmann and the temperature that we commonly have. And we know that this is actually inverse to 1. What this actually tells us is that the number of atoms within a given energy level should be equal or less than the actual degeneracy levels that there are. Degeneracy is a little bit of a hard concept to explain. However, I'm going to make the best possible to explain it to you in the next section. For the case of fermions and bosons, however, we are confused with the levels of energy than say exactly how many atoms are there. So we have to rely on a different formula. You will see that the new letter intruded right here is this little mu letter. This mu letter stands for chemical potential. And we can actually work out how to get to this formula based on the previous distribution. First of all, we need to explain how many states are we talking about, because this actually needs to talk about the Bose-Einstein distribution. You see, Bose-Einstein distribution works a little bit something like this. Imagine that you have this whole energy level called epsilon. We can know how many atoms are in here just based around the amount of degeneracy states that it has. Degeneracy is usually represented by a G, and we can imagine G like the number of rooms that are in here. The rooms can be divided into separate spaces just by walls. The amount of degeneracy is essentially the amount of walls that are in here plus 1. And then in there we can arrange how many atoms as many atoms as we want, and therefore we can also find out that we can figure out the amount of arrangements that we can say in here, just mixing up atoms and walls all together. The total amount of arrangements that we can get from all of these walls and all of these atom configurations can actually be summed up into a factorial function in which we can tell exactly how many ways we can arrange each of the things. It's just saying how many times are you going to take one of these atoms or one of these walls every time that you need. And from here you could actually say to yourself, what if I wanted to specify how much change I have exactly in this formula? Well, what we could actually do is try and derivate this thing based on the change of number of atoms that we can have and try to minimize this thing as much. And we also want to do it so that the change of the particles is actually equal to 0. We do not want any changes because we want to tell exactly how many particles we can have in that same time. Also, along with that, we also don't want any chemical reactions with that. So we can also make it so that the sum of all the potential energies in the system are also 0. Based on this, we can actually make a function based on how many states we can actually have, and all of we have to do is base a function around the population that we do wish to have, which is a massive factorial function, and every single product right after that. We also have to remember the simple rules that all the population must equal certain number of atoms that we already know that are in the system, and that the sum of all the potential energy levels in there are also equal to a finite amount that we already know. So with that in mind, we can actually get to a lot of derivations straight from the get-go. If we actually get the natural logarithm of this, we can approach a value here that is something close to the and it approaches that similar equation in there. However, we can set up some rules of what we want according to all of these levels. For example, what if we actually change the values of this and this in order to make it fit into us? What we can actually do right now is try and make everything into a single derivation in order to know how much we would change according to the population. So all we have to do is make a little derivation right here, and all the equation is going to come right after. Or what we have already here, we know that the derivative of all of this so all of this comes out perfectly. However, we set up some rules beforehand. We can already tell that we have a finite amount of atoms and we have a finite amount of energy. So what happens if I derive those? We know that this is not going to change. So in layman's terms, whenever we try to explain that, we have to change all of this part of this, and the change would actually be equal to 0. This gives us two very powerful tools: are that the change of the atoms must be equal to 0, and that the change of the energies, in this case, must actually be equal to 0 as well. And this actually is going to concise everything inside the formula into something very small, which is actually gets down to this formula. Now, as you can see, this side and this side are actually differentials. That means that we can actually make an integration over them and figure out exactly what are the values that we need. So you might have a question over what is alpha and beta. Those are called Lagrange multipliers. These are just used in order for us to figure out what are the future values. Later on, you will understand what values that this takes. But so far, let's move on with the rest of the formula. If I manage to equate everything in the formula just to be equal to 0, for this case, it would actually be that's a little bit of AI plus GI over EI, it's actually a pretty long one, plus whatever is the value of alpha plus beta with every single energy level must be equal to 0. And we can actually figure out exactly what is the population out of this, because all we have to do is isolate Ni from the formula. So solving for Ni, we are actually going to do the following. We are actually equating everything in terms of Gi, and the terms on the top are actually going to go on top of Euler function minus 1. What does this mean? That means that our total population is actually going to depend on the degeneracy stage, also known as the amount of rooms that you can have in order to allocate all of our atoms. divided by these two constants to a power of Euler minus 1. But what are these constants still? Well, let me tell you something. The power of these constants is actually determined by a formula that we already figured out in the past, which is actually the previous Fermi-Dirac distribution. So what this means is that our final distribution should be based something along the lines of whatever the Boltzmann constant and the temperature are actually telling us to do. And this is where the Poincare comes in, because now we can equate everything. And alpha and beta, we actually know the values for that. The values for that thing is actually epsilon I over constant beta minus 1. We're just missing one little thing right in the formula, which is actually this little constant called B. This constant right now can be defined as Euler to the power of a negative power of energy. And it's just the remaining amount of energy or potential energy that we can describe within the formula. We obviously want it to be a low value just so we can tell how many atoms are possibly in there, because at higher values it's actually easier to just say that it's 1. The value rounds out so much. So in this case, the final interpretation that you can give to this is that for low values of Gi, you can actually say that there is a small amount of particles, and for higher values of degeneracy, you can actually think that there's a lot. However, in these cases, we actually work on spots in which you cannot actually tell how many ways are there to sort each another of the atoms. It's usually kind of hard to tell how many groups there are. But in the other cases in which we have a lot of ways and allocations, we can actually say that there's a higher number of atoms. You just have to tell yourself how many ways can we arrange this, and everything should fit down to this distribution. So you might be asking to yourself, why is it important that we actually can't confuse atoms with other atoms, based on that we're scientists and we should know exactly how one thing is different from the other. In this case, why do we confuse atoms and VE condensates? Well, that's a pretty good question. However, it all relies on the thing that we know as a wave function. Under the conditions of normal particles, we usually have what is described as a wave function, the emission of energy that the own particle does by itself. This is what we commonly use in order to distinguish any particle from one another. So let's take an example in which you take two particles only, and each of them has a different wave function. We plot each of the wave functions, and we can say this one has epsilon 1 and epsilon 2 function. If we try to put these both particles into the same states, we could actually do the following and add both functions up. But if we add them up, it actually turns out that they add up to 0. This is actually very important because it allows us to distinguish one from the other with normal distributions as shown below. However, when we jump into Bose-Einstein condensates, the story kind of changes. Now, if we actually wanted to put both of the particles into the same state and add them up, we actually have a little bit of a problem, because when we superimpose these two waves, you don't actually get 0. You get a totally different wave, but you cannot actually get plenty of information from that. And that is actually troublesome. We cannot determine what is the basis energy level of this thing, and ergo we cannot even say how many particles are there, because all of them will collide, will not add up to 0 when we try to combine them, and we essentially can confuse them with other energy levels, and it could say as much as say that there's only one atom there. So this is talking about all of the particles together acting like some sort of super atom. Don't take my word for it, but that is actually pretty cool if you think about it.